Hello, we are Group 2, and our topic is going to be on Integrated Sensing and Communications, or ISAC. So, for introduction to ISAC, that stands for Integrated Sensing and Communication, and it is a framework that integrates wireless communication and radar sensing into the same hardware. More specifically, it allows for hardware, spectrum, and signal waveforms to be used simultaneously for both sensing and communication. Therefore, ISAC is a system that ISAC allows a system to sense its environment such as motion, terrain, or obstacles, and simultaneously communicate data and information over wireless links and perform these actions at the same time over the same signal. This overall saves energy, spectrum, and cost. And as you can see on the figure on the right, we have a base station which both communicates with users and senses targets. The users are typically receiving data via wireless methods such as 5G, and the targets are being sensed. As you can see, ISAC uses both radar and communication in the same system. And in general applications, this typically allows for vehicle tracking, gesture recognition, and occupancy sensing without needing to separate radar equipment. In our project, a reconfigurable intelligent surface, or RIS, is added to this. So, what is RIS? A reconfigurable intelligent surface, or the RIS, is a programmable surface structure that can be used to control the reflection of electromagnetic waves by changing the electric and magnetic properties of the surface. These surfaces can be placed on the radio channel between a transmitter and receiver to control how the signal reflects off of a surface and its propagation path. They're used to basically steer signals to the receiver for better reception or link quality. And as you can see in the figure, there is a base station or transmitter that sends signals that aren't directly aimed at the receiver. The RIS is shown with the title or pixels, which adjust the phase and amplitude of the signal. This is controlled by an FPGA or microcontroller, which changes the beam direction exactly to the receiver, which could be a phone, IoT sensor, or vehicle. We can implement RIS using either metasurfaces or antenna arrays, but our work focuses on antenna arrays. So, for DOA and beamforming, when a signal travels through space, it reaches different parts of an antenna array at slightly different times depending on the angle it arrives from. And as shown in the image here, a wavefront from angle theta reaches the first antenna, then the second and third, and so on, where each is delayed by a distance of d times the cosine theta. This results in a phase shift used to estimate the angle of arrival, aka direction of arrival, or DOA. And beamforming, on the other hand, is the process of shaping the antenna array's transmission pattern, like if we were just adjusting the focus of a flashlight to target a specific user or a target known as a DOA.
This is a conceptual image of the RIS-assisted DOA estimation system, and it's the base system model from our paper. On the left, you see the access point, or AP, which emits regular communication signals. The RIS is the top center, mounted on the building, which dynamically adjusts its phase shifts to manipulate signal directions through some programmable controller like an FPGA or microcontroller, like we mentioned earlier. There are several buildings which are our targets. The AP signal bounces off the RIS, interacts with the vehicles, and then gets scattered. The RS reflects the vehicle's signals down to a sensor shown on the house, which only has one receiver channel. The red line from the RS to the sensor is interference, which is suppressed by the author's system. Overall, the purpose of this model supports passive vehicle tracking without the vehicles needing to send any signals themselves. This makes it a good addition to autonomous driving, traffic control, and smart intersections. Multiple signal classification, or MUSIC, is an algorithm for DOA estimation that separates the signal and noise subspaces of the received data. What it does is it collects snapshots of the received signal across antennas to improve resolution. Hankel-based music implements DOA estimation with just one snapshot since standard music requires multiple. The authors did this for real-time and snapshot limited scenarios. However, we plan to change this in our contributions. Lastly, the root mean square error is the average difference between our estimated DOAs and the true ones to measure performance. The lower the RSME, the better the estimator. The Kramer-Rao lower bound is the theoretical limit, which tells us the best accuracy we could hope for under ideal conditions. If our RSME is close to the CRLB, we can use that to determine if our method is efficient. In our project, we used RMSE to evaluate our results, then CRLB to benchmark them. This helps show how good our results are and how much better they could be.
Okay, now here we have the paper's original results, without any modifications made to them quite yet. On the left, you can see the beam forming pattern. The blue curve represents the power response of the optimized matrix, where there is a sharp dip around -10 degrees corresponding to the direction of the access point. On the right, we have a spatial spectrum, which is generated using the proposed atomic norm and music method. The blue curve shows how strong peaks at the actual locations of the targets, with the orange stems being ground truth DOAs. And now if you look on the very right, you can see the performance metrics for this initial test, showing the root mean square error of 0.0955 degrees. This means that the average error between the estimated angles and truth DOAs are less than a single degree. Additionally, the RMSE is relatively close to the Kramer-Rao lower bound of 0.02117 degrees, showing the paper's high performance. However, we feel there is still a slight gap in terms of optimizations between these values, which we hope to build upon, especially when you look at the ratio to RMSE and CRLB. Now, if we move to the next slide, in terms of our contributions, in order to build on the initial results from the paper, we introduced two contributions to the DOA estimation framework. First, we added support for multiple snapshots, since the original is based on Hankel methods and just a single snapshot. And by incorporating multiple snapshots, we hope to average out the randomness and achieve a much more stable, accurate estimation of DOA. Additionally, we implemented a fast Fourier transform-based method for DOA comparison as a method for comparing our results. The original GitHub code, though, only included the atomic norm minimization as well as the Hankel music methods, so we added an FFT-based DOA estimation as a fast, low-complexity baseline. This is going to help with benchmarking the performance of more advanced algorithms against a familiar technique. The FFT is essentially an additional way for us to gain an idea of the locations of these cars based on a much quicker means of testing. Thank you.
So this slide shows the results of applying the FFT-based DOA estimation method. As you can see, the blue curve represents the power spectrum generated using beamforming techniques, whereas the red stems show the actual ground truth DOAs for the three vehicle sources. While FFT is computationally efficient and easy to implement, the spectrum is clearly noisy, as you can see in the figure, and shows many side lobes, which makes it difficult to pinpoint the exact source directions. This is due to the limited resolution of the grid and the small number of RIS measurements used. But despite this, we implement the FFT method as a quick benchmark to compare with more advanced methods like the atomic norm minimization, which was used in the paper. And we'll compare the performance quantitatively using the RMSE values that was mentioned earlier. So this slide shows the improvements that we gained through the implementation of multi-snapshot averaging in our DOA estimation system. On the left figure, we have the response of the optimized measurement matrix. The beamforming pattern shows a strong peak aligned with the AP direction at around the -10 degrees point, showing that our measurement matrix is effectively focusing energy. And on the right figure, we see the spatial spectrum generated using the atomic norm minimization method. This method shows sharp peaks similar to the original paper's results that match the ground truth DOA shown by the red stems. However, our solution shows an improved resolution with a root mean squared error of 0.1309 degrees, while the lower bound, or the Kramer-Rao lower bound, or CRLB, is 0.0554 degrees, which means that we're approaching the theoretical performance limit, showing how effective the combination of snapshot averaging and sparse recovery is for a high accuracy DOA estimation. For future work, we hope to optimize these parameters in the code once more to get the lower bounds and RMSE even closer if that's possible. In addition, we hope to explore other comparison methods such as the L1 norm sparse recovery, which was talked about in the paper, and other methods or other baseline methods that was also mentioned in the paper that we didn't get a chance to look into. This is because the paper only, or at least the code only, supports atomic norm and the Hankel-based music method, and our implementation from this presentation recently added the FFT method, so we would hope to continue to add more baseline comparison methods. On top of this, we would want to apply deep learning models for a data-driven DOA estimation approach, since traditional methods like the FFT and atomic norm rely on model-based assumptions such as the structure of DRA and current noise statistics. But deep learning offers a data-driven approach that can learn to estimate directions from raw or pre-processed measurements, even with the presence of noise or interference. For example, a convolutional neural network, or CNN, can be trained on spatial spectra or correlation matrices to learn patterns associated with DOAs, while transformers can be used in a dynamic setting such as mobile vehicles. Overall, deep learning and machine learning would help in our RIS-based DOA estimation approach by adding variation to our tools that we can use in those calculations. But that was all for our presentation. This is our primary reference, as well as a link to our GitHub repository containing our final code. And then these are the references that we used for the photos in our presentation. Thank you.